With a history of high damage to deep infrastructure and also the highest civilian casualty rate of almost any other type of combat, strategic bombing has become one of the most valuable forms of aerial combat, especially in the beautiful year 1943 where this video is taking place. Strategic bombing is, as it sounds, bombing things strategically. In a way, it's a strategic move to make an enemy railroad, factory, or any other facility that may be of strategic value not exist. Not to, of course, be confused with terror bombing, which is a term used for when strategic bombings, such as Dresden and the Blitz during the Battle of Britain, are so deadly to random civilians that they also completely cripple a country's morale. The mission of your average strategic bomber is pretty simple. Step 1. Take off from 1,000 miles or kilometers away. Step 2. Bomb target. And Step 3, the hardest step, go home. The American strategic bombers of World War II tried to modify this plan slightly by instead replacing Step 3 with dying. You see, the Americans preferred daytime raids, and much of their strategy relied on high-altitude, highly defensible bomber aircraft such as the B-24, that could fly high above those German interceptors. The American strategists, however, could not predict this one thing. It's the big guns that point up. Yep, that's it. A very high amount of American bomber casualties during the war was due to German flak guns. The 88mm and 128mm, heavy anti-aircraft artillery guns of the war. The flak cannons could be used for shooting down planes, just as well as anti-tank and anti-bunker activities. Yet these guns just kinda shot at everything. This was a detriment to American bombers, who insisting upon daytime raids were more or less like shooting turkeys in a barrel for the German anti-aircraft operators. Even in the nighttime, while less common, the German flak guns were able to fire upon bombers using radar targeting to confirm the general, non-visual position of the bombers. Or in other words, slightly better than blind fire. Some people claim the daytime raids stem from a moral standpoint of seeing the target you're bombing better. But Americans also killed plenty of civilians in their bombings, just like everyone else. Hey guys, I don't know if you know this, but there's this thing called jet stream that exists, and it'll probably blow your bombs off course, and by probably I mean definitely. The 8th Air Force found that only 1/4 of American bomber crews survived their first 25 missions, the remaining 75% dead, injured, or captured. America instead found more success in firebombing Japan, where the total civilian deaths and destruction was greater than that of both nuclear bombs dropped combined. Germany, on the other hand, as well as Britain, favored night bombing instead. During the Blitz, German bomber squadrons would allow a radio beam from one station until they intercepted a high parallax radio beam from another station, which was also aimed at the target. After this second radio beam was intercepted, they knew to drop their payload, even if there was absolutely zero visibility on the target. They would then fly home, usually unscathed. That is until the Brits figured out what a radar was. An estimated 40,000 civilian casualties were documented from this bombing. Yeah, you know, almost every major offensive strategic bombing involves more civilian deaths than combatant deaths. Anyways, we'll be taking the design philosophy of all these countries and their strategic bombers to make our aircraft. As it turns out, this isn't exactly a history video, it's more of a flyout video. Maybe I'll do documentaries in my free time so I don't spend 3 weeks between releases. Let me know what you guys think of that in the comments below. Either way, as mentioned before, this bomber was designed to fly in the wonderful year of 1943. Just so you guys know, this is about 1 year after the first flight of the famous B-29 Superfortress bomber. In the year 1943, most bombers could go higher, faster, and incorporate bigger payloads and more advanced technology than ever before. This year, along with every other year in the entirety of World War II, were fascinating yet horrifying years in the development of strategic bombers, which might just be the most deadly weapons ever used in war. So far. But we'll be combining the doctrine, designs, and civilian casualties of all strategic bombers from all nations to design our very own long-range strategic bomber using Flyout. Using this complicated building simulator, I'll be building a full-flying 3D model of our bomber in a reasonably realistic environment. If you want to download and fly the vehicle yourself, I'll leave it available for download in my Discord server. The link will be in the description below. And for more information on the game, I'll also have the Flyout server linked. Let's get on with it though. We'll be splitting this video into 6 major parts: the blueprints and design requirements, engines, airframe, flight model, weapons, and finally a test flight and conclusion. Feel free to skip around to any of these parts in the video. I'll give it a solid 30% chance. I'll include timestamps in the comments and description. Part 1. Design specifications. To understand what we want to build, we need to understand different methods of bombing during World War II. There was dive bombers, light bombers, heavy bombers, daytime, nighttime, low altitude, high altitude bombers, photo bombers. Dive bombers and light bombers were shorter range, lower altitude, light and agile bombers that could quickly change locations, take off from shorter airfields, be kit bashed into awkward night fighters, and of course, provide strategic advantage to a nation. These bombers, such as the PE-2, or as I will refer to it, the Peshka, could also be repurposed as heavy and night fighters due to their nimble airframes. They often fought in battles, destroying emplacements or tanks as their precision specialties and high agility allowed for precise and quick bombing of frontline targets. Heavy bombers, on the other hand, were designed to carry very heavy bomb loads over long distances. These bombers often flew at a higher altitude and conducted major raids over cities, factories, camps, and railroads far behind the front lines. These bombers, such as the B-24 Liberator and the Avro Lancaster, were famous for taking out strategic targets such as factories and entire cities in massive bombing raids involving hundreds of these aircraft. Day bombing, as it sounds, is simply attacking these targets during the daytime. Night bombings, however, often use radio beams, radars, and glowing markers to designate targets. Alright, let's talk about what I'm going to be doing now. I spent almost 30 hours and about 900 parts building this thing. Because I have no life, I'm sorry. This heavy bomber would need to be able to carry at the very minimum 6 tons of bombs. The GT-B-18 Marksman also needed to prioritize speed and altitude, flying at a minimum of 9 kilometers high, or 29,527 Freedom units for the Americans out there. A ferry range similar to that of the B-29, the GT Marksman needed to be able to travel at least 8,000 kilometers to ferry between continents easily. And this thing won't just be a bomber, it'll be an entire mobile fortress. Radar, remote turrets, a pressurized command center, internal communication phones, and defensive armaments mean that this bomber can fly on its own, day or night. The bomber will be flying for a glorious United Bow Air Force during the Second World War. To make our historical vehicles, I slapped a country into the middle of the Atlantic Ocean to mess with global politics. We made Henry Ford's America, but somehow 10 times worse. Our nation will be primarily conducting night raids over Europe, the distance to Germany being a traversable 3,000-ish kilometers, or about 1,619 nautical miles. Fun fact about nautical miles, by the way, and why it's my favorite unit. Each nautical mile is exactly 1 minute of rotation around the Earth. That means that every 60 nautical miles is exactly 1 degree of travel around the entire planet. But either way, getting back on topic, that's a pretty short distance, so he should be able to conduct raids on Germany without needing to land. Part 2. The engine. Any good build starts with a good engine. Combining aspects from American and German engines, this turbo-supercharged 14-cylinder behemoth radial engine accomplished all of our altitude and speed goals quite easily. Most internal combustion engines work on internal combustion. The two things you need to increase power are more air and more fuel. You need both at once. The fuel part is pretty easy, just squirt more fuel into the cylinder each time. The air part, however, is a little bit more difficult. The easiest way to introduce more air is opening the intake or introducing forced induction. The problem is, air density drops a ton with altitude. At this thing's cruising altitude, the total amount of air present is about a quarter of what it is at sea level. To deal with this, the turbocharger helps cram extra air into the manifold, keeping air pressure high in the engine. The turbo works by using the waste energy from our exhaust gas to turn a turbine. The turbine wheel spins a compressor, which in turn forces a bunch of extra air into the engine. For a net zero loss, of course. It's just using all that spare exhaust gas laying around after all. However, there is one problem with this setup: heat. Exhaust gases are where almost all of the engine's heat is dissipated through. And when they turn that turbine wheel, some of the excess heat can soak into the intake manifold. And much like a baby in a hot car, our engine will die from significant heat soak. This can cause things like engine pinging, where combustion timing fails to reach the apex, causing a loss of power. Now to solve this, I have 2 solutions. Solution 1, exhaust cooling, and Solution 2, intercoolers. By running the exhaust outside the plane before it reaches the turbo, it helps to cool it off. This reduces heat soak, or better known as any excess heat from the exhaust gases, increasing your induction temperatures. On top of this, a radiator-like device was added after the turbo induction system to pre-cool the air before it reached the rest of the engine. This is known as an intercooler, as it cools the air in between the induction stages, keeping our engine running smoothly at any altitude or airspeed. Because of all this power and all this boost, if we used it all, our engine would have enough power to send a piston into low Earth orbit. In order to not turn our internal combustion engine into an external combustion engine, we dumped all of our extra boost out just before the manifold, instead only accepting 1.4 bar of pressure. This means our engine only uses the extra boost when it needs it, keeping the same power up to the frigid altitudes of 10,000 meters, or about 33,000 feet. As a quick side note, almost all bombers did this to some degree, as well as almost all fighters. So here it was, my beautiful, complete engine, carefully optimized to reduce the load on the computers for all 3 people who download this thing. Please download it, please, 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 please. The game resets all textures to high resolution when I imported the engine, however. To make sure I don't brick everyone's computer, I had to go through and once again manually change each resolution back to none. Fun! The engine was a blend between the American double wasps used in high-altitude bombers, as well as some styling from experimental high-altitude aircraft of the Germans. As far as I know, those were the only 2 countries to experiment with turbochargers, so I guess it makes sense. Of course, ignoring the glorious UFB's turbocharger experimentation. Part 3. The airframe. Alright, so there are a ton of different shapes and sizes for bombers, so how would we choose which one is the best? Well, first things first, we start with this fun aerodynamic concept known as induced drag. Essentially, chunky, thick wings, assuming the same wing area, produce an exponentially higher amount of drag than their skinny wing counterparts. Despite producing the same amount of lift, the lower aspect wings produce more drag. As the vortex travels down the wing to the tip, the vortices of these chunkier wings will be larger than those of a skinny wing, sort of sucking the plane backwards. This is why gliders and all high-altitude planes generally have very long, skinny wings. This is referred to as a high aspect wing in aviation, and it was almost exclusively used on all high-altitude bombers of World War II. This is one of the many reasons why aircraft such as the B-29 could fly far higher than aircraft like the HE-111 or Peshka. Having these high-altitude wings also increased our lift-to-drag ratio, meaning that we'd need less power to stay airborne and therefore we could go even further. At the end, our aircraft had a lift-to-drag ratio of approximately 13.2. Meaning that we flew slightly better than the B-24 at 12.9, but notably less than the B-29, which was about 16. This was to be expected, as our aircraft had features such as radars, greater cooling area for the engines, external exhaust, as well as a different fuselage and empennage design that would have realistically increased our vehicle's drag from the B-29. Anyways, now that we had a lift-drag ratio and working engines, we were able to test our vehicle's maximum range. This was at the end, of course, so I'll save that for later. I also included custom landing gear on the vehicle, which was super nice for the actual design, as the stock in-game gear sort of sucks. These gear systems generated perpetual motion backwards and actively increased my takeoff run to nearly impossible though. Because more or less the game just doesn't like the physics of the joints on the landing gear. So for takeoffs we had to abandon the custom landing gear down the line. Featherless? Biped? Behold, a man. Using our 4 twin-charged air-cooled engines, I also positioned our tail as an H configuration over the engine slipstream. I did this because the air from the engines is pushed over the rudders, giving a boost to the air deflected, and therefore your rudders can work better. Part 4. The flight model and control surfaces. After this, we were finally able to move on to the control surfaces. You see, my plane used an advanced building technique us in the flyout community just call, lying. A fuselage piece is put over the position of the main wing so you can set a custom resolution and wing shape to a higher fidelity than what the stock wings have to offer. As a result, I need to manually edit each flap, aileron, elevator, tail, wing spar, and fuel tank, along with the invisible internals to generate adequate lift and drag for the wing. Between all this nonsense, the symmetry glitches of the game, and the overall complexity of the animation rigging, this part easily took me the longest. I spent about 2 or 3 hours straight just getting all the control surfaces right. This includes animations for the flaps and controls, trim tabs, push rods, and custom fuselage pieces for each control surface. Oh geez, Messier, I wonder why this build took 30 hours and 1,000 parts. Yeah, it's pretty obvious. Maybe I went a little bit overboard with this one. Anyways, now while I build this and struggle in the background, let's talk a little bit about World War II control surfaces. While things like trim tabs could help reduce deflection, things like hydraulics were still pretty new, but majorly helped out pilots. Without needing to actually be the buffest human alive, even John Soy could turn a bomber and deflect its control surfaces with minimal problems with these hydraulics. Aircraft such as the B-17 and B-24 were known for having hydraulic systems to assist the pilots with maneuvering. Next, due to extreme altitude capabilities of our aircraft, a fully pressurized cockpit was used on the vehicle. As long as they weren't being turned to Swiss cheese while doing a daytime raid, our crew could enjoy their time and sip their piña coladas while flying to their target. Beverage flying is a sport in our glorious country, by the way. Part 5. The Weapons. Alright, here's the wildest part of the video because we'll be talking about two different nations I took the most inspiration from tactics. And by the two nations, of course, I mean Britain and Britain. I mean, I guess for the engines and bomber design it was more American, but I also included radars and nighttime operation equipment. Honestly, this bomber doesn't seem that realistic. Spending money on the high altitude engines but then conducting night raids doesn't seem very cost efficient. Although I guess it would save more lives, so at least there's that. Yeah, if you can't tell, one of the primary purposes of this aircraft will be night bombing. The radar and marker and radio beam guided night raids proved far more successful than the day raids of the time, especially over the heavy AA protected mainland Germany. This means, similar to the British, we would need a radar. Night fighters and night bombers almost always use some form of radar. Taking inspiration from the Lancaster, the GT Marksman included both front and back facing aerial warning radars. On top of this, there was an underbelly air-to-ground radar for precision nighttime bombing outside of the range of radio navigation towers that we mentioned earlier. One of these radars used in real life was the H2S radar used on the Avro Lancaster. Originally developed and put into service in 1943, it saw service all the way up to 1993. Wait, so you're telling me that the same radar initially developed for World War II was used on the Vulcan? You can't really say that though, because it's more or less the radar of Theseus. However, this also involved making the bomb bay. Towards the end of World War II, specifically in the raids of Hamburg, American and British scientists worked together to find the best ratio of incendiary and high explosive bombs to destroy the town as much as possible. Flying over the city of Hamburg, over 700 aircraft had dropped their payloads in under 1 hour. The entire city appeared to be on fire by the time the clock struck midnight. The harbor, waters, and streets all appeared to be covered in flame, burning so intensely that almost nothing survived. During the pathfinding and first wave of the raid, aluminum flakes were saturated in the sky. This would confuse German radars, and this is one of the first examples of what we now call chaff being used in combat, allowing the night raids to be conducted with almost zero aircraft loss. These downright horrific technologies would be included in our bomber as well. A payload of 8 tons of upscaled SC-500 bombs to represent our bomber payload. On top of this, due to the pressurized crew spaces in the bomber, I found extensive use in remote turrets, save for a singular tail gunner. These turrets, similar to the remote control systems of the B-29, were designed to specifically allow a safer operation of turrets through remote observation glass, allowing the cabin to be pressurized and the crew to be relatively safer. After all that, it was polish. Things like minor panel gaps between the elevators and trim tabs to make things look more realistic, a basic interior that is mostly focused around the cockpit, as well as a whole plethora of minor things such as landing lights, antennae, and a small crawl space for the navigator and bombardier. After all this was completed, it was finally time to fly out, so I'll tell you guys about some of its stats in the air. Did it reach my goals? Let's do some math on the engines. With a specific thrust, aka fuel flow divided by thrust, of 8.7 grams per kilonewton second, along with a cruising speed of about 137 meters per second, a lift to drag of about 13, as well as a fuel fraction of 0.25 with bombs or 0.37 without, we were able to plug all these values into the Bridgewet range equation. Link in the description below for the Desmos tool. Using this equation, we could input these values and get an almost perfect answer, which was only slightly off because it didn't account for specific thrust or lift to drag changing with reduced weight. After plugging these values in, we had a range of about 6,000 kilometers with bombs and almost 9,000 without. I'd love to break down this equation to show you all how it works, but I only have so much time in this video. This absolutely blew my range and speed goals out of the water, and it almost seemed over-engineered. Honestly, that's been my mood regarding the entire aircraft, a little bit of overkill. Like, if it's meant for night raids, why would it have such powerful altitude engines? Or the full cabin pressurization? I wasn't too sure myself. Either way, as you were watching the montage, you could see a few different variants of the vehicle. The one shown in this short climbing time-lapse is my final iteration, the main difference being the bottom turret positions. This variant includes an underbelly front-facing turret, whereas the other variants did not. It would be controlled in the same area as where the Bombardier sat. The climb rate of the vehicle was around 5 to 6 meters per second with bombs, but surpassed 10 without. Otherwise, we are just about done with this vehicle. Once again, my time constraints were the biggest problem, meaning a lot of the parts I wanted to work on weren't being finished so I could get this video out in time, which is still a few days late. If you want to fly this thing yourself, feel free to download my vehicle in the Discord, link in the description below. Have a great day, y'all, and see you on the next one.